This lesson is on simple harmonic motion, which is commonly referred to as SHM. It's quite a technical class. There's a lot of formula and definitions and terms, but between everything, hopefully you'll find it somewhat easy and easy to learn. So we're going to start off again looking at a spring, and we have this work on the right to help us through that. So taking a look at the diagram to begin with, the spring is first off in its equilibrium positions. That will be kind of still, stationary, or as we're going to look at it, kind of in the middle. So this is the length that the spring would have with this mass on the end. If it's moving and it goes all the way up to be compressed as much as it can, it's up at this position A. If it bounces down and goes as far down as it can go, that's going to be at position B. So if we think this would be at stationary, or it will be in the middle, so to speak, as it goes from A to B and B back to A as it bounces up and down. And that bouncing up and down is basically simple harmonic motion in a nutshell. So the diagram shows a mass on the end of a spring oscillating, which is moving up and down. That's going to be one of our key words for this lesson, oscillating. It just means moving up and then down again. So if you start off at A, it will be down and up again. That will be one full oscillation, one full cycle. So any body that moves around a central position is said to undergo simple harmonic motion. There's plenty of examples of that, but the mass on the end of a spring is the simplest one for now. So we need to know the particulars of this diagram in terms of distance, energy, velocity, and acceleration at each point. We don't really care about some of the intermediate term points, but at the top, the bottom, and the middle, they're the most interesting ones. So when we start off with this position 0, there its displacement is 0 because it's its natural position. It's no extra stretched, no extra compressed. As it's coming back up or as it's going down, this is where it's going to have its maximum velocity. And we'll look at that in an example very shortly. Because its velocity is the maximum at the middle, that's going to lead to it having the biggest kinetic energy. If we go back, our kinetic energy is a half mv squared. That's our formula for kinetic energy. So whatever it is, it's going to be at the maximum when it's at this position 0. Because all of its energy is kinetic, we have none left for potential. Here, again, if it's left here, it's not going to automatically extend or it's not going to shrink up. So there's no potential energy, it is only energy due to movement. And that's true whether it's going up or down or it's just stationary. It still have some gravitational potential energy, but just for the system, it will have 0 potential energy. At A, so when it's up at the top, it has a maximum displacement. So it's gone from the central position all the way up as high as it's going to go. Its velocity then is stopped. And again, it goes up, up, up. Then it comes down, down, down. In the middle, it's going to have to stop. Its velocity then is 0 meters per second, which means by, again, this formula, V is 0, so it is no kinetic energy. So all of your kinetic energy has got transferred to potential energy. And we have the same situation at the bottom. When it's at the bottom, it's got the maximum displacement. It'll go from going down to going up. So then it must stop in the middle, so velocity is 0, so the kinetic energy then is also 0. So that's very important that we know that. Again, they tell us up here the force and the acceleration are at the maximum, velocity 0, force and acceleration 0, velocity at the maximum, and then back, like the top case, force plus acceleration maximum with velocity 0. So we have then the definition for this before we go looking at our simulation. So the definition, a body is said to be moving with simple harmonic motion if its acceleration is directly proportional to its distance from a fixed point on its path, and its acceleration is always directed towards that point. So in this case, as it goes up, 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 the speed is going to be slowing down. The acceleration is always going to be towards center. We know it accelerates towards center because it's going to have its maximum speed at the center. So as it's coming down, the spring is pushing it. And the spring pushes it, gives it that force, it gives it that acceleration. But then once you cross this middle position, the spring is getting overly stretched. So it's going to be going slower, 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 slower. It'll get to the bottom, and that's as far as the spring goes. Then it will stop, and then it's going to spring back up like Wile E. Coyote, all the way up, and it's going to be accelerating, accelerating, accelerating. Then you get to this point, and again the acceleration is going to slow down as the spring gets more and more compressed. It's less free to move. It's getting more compressed. You're reaching the limit of what it can do, and it's going to go here. So again, that's your definition. That's something you need to know. I'm going to take a look now at the simulation. So we're back here to PhET simulation. So I've set this up with energy. So it's going to take, we can't take snapshots to take a look, but we have the mass hanging on the spring. So I've got all of these set up, and I actually put gravity to 0 just to make our situation a little bit more simple. So if we pull this down and let it go, this is going to move at simple harmonic motion. So it's got that displacement that's going up and down, up and down, up and down. So that's our basic thing. That's our first thing to look at. That's what simple harmonic motion is. We take a look then along the graph. It might be difficult to see, but this first one is for kinetic energy, so energy due to movement. This one is gravitational energy, so the potential energy due to gravity. Because I have gravity at 0, that one should be 0. Then we have potential energy due to the spring, so that's due to the system. So as I pull this down, you can see that blue is going up, because if I release this, it's going to go flying. So that's the potential energy due to the position, the potential energy due to the spring. Similarly, if I go up here, it's got more potential energy because it can push itself down. It's going to start accelerating, so that's got a lot of potential energy. This black line here is the center of mass, so that's where it kind of hangs in a normal situation. So that's what's called the mass equilibrium over here. We can later on we'll look at some other things, but for now we're going to take a look at the velocity. So as I compress this up and let it go, we can see the velocity. So the velocity is moving up and down. The size of the arrow indicates how quick it is. And we can see at the top and at the bottom, this arrow shrinks to 0. So the arrow is the biggest in the middle. It changes direction from up until down and from down until up. So that shows it stopped in the middle. So that's my velocity. Biggest in the middle, smallest at the top and bottom. Acceleration then on the other hand, we can see the acceleration is always towards the middle. That's a key point. And the acceleration is biggest at the ends. The acceleration is 0 in the middle because that's at the highest speed, so it can't accelerate anymore. If it accelerated more, it'll be faster. So the acceleration is most at the top and bottom, and it's least in the middle. So again, this helps you show that it's changing direction, and it's biggest at the top and the bottom, again equal. There is this thing here called dampening, which means that it's going to stop. If I took the dampening off, then it should bounce up and down. There's no gravity, there's no dampening, so it should bounce up and down like that forever. And this is actually a bit easier to see. So that we have at the top and the bottom, we have the biggest acceleration, and we have no acceleration in the middle. So that arrow switches off, so to speak. If I show it again, I can show the two at once. We'll squash it up, no dampening, no gravity. So it's going to continue on forever. And we can see as the green velocity arrow is big, the yellow acceleration arrow is small or gone, and vice versa. At maximum acceleration, you have no velocity. It happens at the top and the bottom. At no acceleration, you have maximum velocity. So that's what we have here. So that's our system. Now, while it's going there with no dampening, which is perfect, I can see how the kinetic energy changes. At the top and at the bottom, we have no kinetic energy. So the top, bottom, the kinetic energy is gone. When we're in the middle, we can see that we have the most kinetic energy. Then we have this transfer between kinetic and potential. So when one is at the max, the other is at 0. When the other is at the max, that is at 0. And we can see here the total energy. There's no losses because of this dampening. When we put dampening back in, we can see that this new force appears. So this is your thermal heat. So this is the friction of the spring. The spring will be heating up. That's what the conservation of energy tells us. Energy cannot be created or destroyed, only change from one form to another. So our kinetic energy and our potential energy die down. So everything is turned to heat. And then we have the total energy is equal to thermal energy, and there's nothing left for anything else. So again, this is our simulation. This is a very nice way to see what's going on, and it shows us exactly what's happening. We can adjust different things. We can put gravity on or off. So again, maybe you want to see gravity, so we could take gravity on Jupiter. Why not? So gravity on Jupiter, and we'll just stop that. So you see this is much too big for Jupiter. We can't see it on the screen, so if we take that mass off, that random figure, we could figure out if we wanted. We then use this mass here, so this is our 100 grams. So we have all of this information again, and here in this position, I'm not sure what happened there, but we have gravitational energy, because this could fall. So that's the gravitational energy. We have 24.8 meters per second because we're on Jupiter. And then we also have the energy due to the spring. So the spring will give it some energy. As we compress it up, now we have a huge amount of gravitational energy. We also have this energy due to the spring. And because gravity is so big, the downward force is more significant. So as we go, we can see the transfers. We get kinetic energy. We have the gravitational energy, which is big because of Jupiter. We have the position due to the spring, and then we get the conversion going into thermal energy. But again, this total energy will equal the sum of all the other bars. Not everything has gone because we're still going to keep this gravitational energy because the mass could fall. It's at a higher potential. So again, not something we particularly need to look at. We go to the moon then, and even that causes that oscillations to start happening. And again, just while I say the term, an oscillation is a down and an up. That is the combined oscillation. So going back to our notes, we have this definition which needs to be known, but we also in physics like formulas. So to get the formula for simple harmonic motion, so we look at how things are affected. So when we look at the acceleration, we looked at our simulation, we can see that the acceleration is proportional to the displacement. So the displacement and the acceleration, they're linked, but they're in the opposite direction. As you pull your spring down, your acceleration is going to go upwards. And vice versa, as you have your spring compressed, it's going to accelerate downwards. So when we give this displacement, this S letter, when that goes up, the acceleration is going to go down. When we pull the displacement down, it's going to accelerate up. So the acceleration is always towards the center. Again, acceleration is our yellow arrow, so that is always towards the center. Regardless where it is, the acceleration goes towards center. So it's also proportional to the rate of change of position. So how quickly it goes up and down, that also affects the acceleration. Obviously, if it changes position quicker, that's what acceleration always is. That's why you got fast cars taking off and slow cars taking off. So when we put these together, we get A is equal to minus omega squared S. So that's the omega symbol we saw from the last section. There's a reason for this, which we'll look at the very end of the chapter. For now, you just got to use that letter again. So establishing the link between Hooke's law and simple harmonic motion is next, but this is our figure here. So acceleration is equal to minus omega squared S, where omega squared is the rate of change of position. So we're going to look a little bit more about what omega is here now, but all of your questions will be answered in the last video. I'll also stop to spell motion correctly, and we have our derivation ready to go. Again, derivations are like your proofs in maths. You need to learn them off by heart, but it's nice to see where these formulas come from, which gives us such confidence in our physics to know that these things are right and that our formulas and work is solid. So if a system obeys Hooke's law, then F is equal to minus Ks. So that is Hooke's law. That's what we proved with the graph from our first lesson. By Newton's second law, and as always, F is equal to ma. So we use this as our starting principles. We know Hooke's law, we know Newton's second law, we've done the graphs, we've done the experiments based on both, so we're happy with these two expressions. So therefore, when a system obeys Hooke's law, so if you have a system that obeys Hooke's law, no plural on obeys, when a system obeys Hooke's law, we have F equals this, F equals that, so we can let them equal each other. So ma is equal to minus Ks. So when we do a bit of algebra, ma equals minus Ks, so we divide across by m, and we can write it like this. Remember, we're trying to show this relationship here. We're trying to show that a is equal to minus omega squared s. So we're setting this up to keep the s by itself, and we're going to replace this thing here. So again, we do just that. We let omega squared equal k over s. So we're going to replace this here with omega squared, and that gives us our formula. A is equal to minus omega squared s. Sometimes you might need to use this formula, so you might be better off using this here, because you might be given the mass and you might be given the spring constant and you might be given the displacement, so you could use it from here, from the basic elements, but typically this is the formula we look for. So this gives us that formula, A is equal to minus omega squared s. So based on our presumptions, any system that obeys Hooke's law must undergo simple harmonic motion. We start with the formula for Hooke's law, we end up with the formula for SHM, so we show that they're linked.